Algebra 2, Chapter 7, Section 1, Power Functions. A power function is any function that can be put into this form: k times x to the p. We call k the coefficient, and we call p the exponent, or we might call it the power occasionally. That's why it's p for power. K because it's constant, P for power. So, some tidbits or facts about power functions. When x is very large, so much bigger than 0, which we might write like this, much bigger than 0, a power function with a higher exponent is greater than a power function with a lower exponent, no matter what the coefficient would be. For instance, if I have 1,000 x and I have x squared, when x is, and maybe we give these names, f of x is 1,000x and g of x is x squared, then when x is really big, g of x will be greater than f of x. Now, it's kind of a subjective statement, really big. What do we mean by really big? We mean so big that this is always going to be true. So, practically infinite, some very large number. A power function is often described by saying that y, or the function f, is proportional to x to the p. So for linear proportionality, we would just say that, in this case, f of x is proportional to x. Remember, I talked about alpha being used for proportional to when we talked about proportional to. So we describe any power function as proportional to. That means we're leaving out the k. Okay, so for this f of x, we could say f of x is proportional to x to the p. For instance, if I said z is proportional to the cube of x, then we could write that z equals k, some k we don't know, times x cubed. Another tidbit or factoid about power functions is, suppose we have two power functions that have the same constant k, so this k is the same in both. Then over the interval 0 to 1, for the input x, the function's output, f of x, is bigger than g of x if and only if the power, or the exponent, for the first function is smaller than the exponent for the second. Let's think about this. So if we had f of x is, we'll use a k of 1 and a power of 1 for f, and if g of x is x squared, so between 0 and 1, f is bigger than g only if p1 is smaller than p2. So in this case, the power is smaller, so f should be bigger than g between 0 and 1. So if we think about that, when x is 0.5, f of 0.5 will be 0.5, but g of 0.5 will be 0.5 squared, which is 0.25, which is smaller. But when the input is bigger than 1, the opposite is true. F of x will be bigger than g of x if and only if the power of the first function is bigger than the power of the second. So when x is bigger than 1, the opposite is true. G should be bigger. And we can see that if we put in a number bigger than 1, f of 2 is 2, g of 2 is 4, because 2 squared is 4. And this is true for any powers, not just 1 and 2. It's a convenient example to help us remember the principle, though. When the exponent of a power function is negative, we often describe the function as a fraction. Instead of writing the negative exponent, we would write 2 over x cubed, which is equivalent. Maybe we should write equivalent to. And in this case, we say y is inversely proportional to x cubed. So if I say y is inversely proportional to x, that's the same as saying y is proportional to x to the negative 1. Same thing if I say y is inversely proportional to x cubed, that means y is proportional to x to the negative 3 by the rules of exponents. So in general, we say y is inversely proportional to x to the n when we have some constant k and a negative exponent, and we say inversely to the positive exponent. And that's the same thing. These are equivalent. So after talking about some of the facts of power functions, let's think about graphing the power functions when k equals 0. So let's get a sheet of graph paper, and let's draw some axes. That'll be our x-axis. This will be our y-axis. Use a ruler to be nice and precise. So we'll label this as x. Of course, this is positive, negative. This will be y. Positive, negative. So let's make the point that it's 1 here at 4 grid cells. So this will be the point 1, 1. And we'll use this at 4 grid cells to the left as negative 1, and 4 down as negative 1. And so here's 2, and 3, and so on. Here's 2, negative 2, negative 2, negative 3, so on. So we're going to graph the power functions. Let's write it down here. And we're going to say y is some power function. So we'll use the expression for the rule of a power function. And k, we're going to graph only when k is 1. So k will be 1. So we're really just looking at y as x to the p. We're going to graph the different powers p. So let's start with some really simple cases. What happens if p is 0? So when p is 0, we get y. When p is 0, we get y equals 1, because anything to the 0 is 1. So let's draw in yellow this special case. When p is 0, we have a flat line at 1. Why yellow? I want it to kind of be in the background because it's a very special one. So let's look at the next one, simple case. What happens when p is 1? Then y equals x to the first power, which is just x. And this is simply means the input and the output are the same. So if we think about, that means we have a slope of 1. We'll go through the diagonal of every grid square. So let's put this one in black. This is when p is 1. We have a straight line. What about when p is 2? When p is 2, we have y equals x squared. Okay, this we can't really do with a ruler very well. And we've not studied quadratics, which is when we square things much. Let's just graph by plugging in some points. So when 0, in fact, if we think about the power functions for a minute, let's think about the power functions when k is 1. We would have, if we put in 0 for an input, we're going to get out 0 for an output. So if x is 0, y is 0. And if we put in 1, we're going to get 1 to the p. And no matter what p is, 1 to that power will be 1. And so this point 1, 1 and the point 0, 0 are in every power function graph when k is 1. Now if k is 2 or 3, that'll scale us up because we'll have 2 times 1. Okay, but for simplicity, we're only looking at when k is 1 to find the shape of the different power functions. So when we plug in 1/2, when p is 2, we get 1/2 squared, which is 1/4. And then if I plug in 1, I get out 1. If I plug in 1.5, then we have 1.5 squared. What is 1.5 squared, you might say? Well, it's going to be 3/2 squared, or 9/4, 2.25. Okay, so that would be this little box right here we can barely see because it's 1 above, or 1/4 above 2. Okay, so that's going to be the shape in the positive x direction. And it's going to be a curve if we were to actually plug in every point. And we'll do a rough estimation of the shape here. Now what about negative? When we have negative 1/2 and we square it, we'll get positive 1/4. Because it's an even power, the sign goes away. At negative 1, we'll have 1, because negative 1 times negative 1 is 1. And at negative 1/2, we'll have negative 9/4 right here. So we'll have this sort of reflected shape of what we have on the right-hand side of the graph. And sorry for the shaky hand. If we connect this with a curve, we'll see this parabolic shape emerge, which is what we call a shape of a cube, of a square like this, of a x squared. It's called a parabola. So this is a line, y equals 1. This is the line, y equals x. And then here we have the parabola. I'll write it over here. Parabola y equals x squared is the name of this shape. So what about, I'm sorry, let's write p equals 2 to keep the power with it. What if p is 3? We have cubed. So we would end up with 0, again, of course, for 0. At 1/2, we'd have 1/2 cubed, which is 1/8. At 1, we have 1, and if we go all the way to 1.5, we'll go off the page here. What about at 5/4? We would have 25 over 16, which we use a calculator to get close. 25 divided by 16 is 1.5 roughly. So roughly here, sorry, here, 1.5 at 1/4, so it's a little bit bigger than the blue line. Okay, and so the shape we're going to get on the right-hand side will be something smaller. And remember, this follows that pattern we talked about on the interval 0 to 1. The bigger the power gets, the smaller the output is between 0 and 1, and the bigger it is after 1. Now the negative side is different though, because it's cubed, we keep our negatives. So at negative 1/2 we have negative 1/8, and at negative 1 we have negative 1, and at negative 5/4 we get our close to negative 1.5. Maybe make it closer to negative 1.5. Here we go. And so the curve we get, let's do a better job than that. Start here at 0, 0. The curve we get will bend through the line, through the dots, and then down we go. So let's put this dot back here. Let's try to connect to the dot here and down. Okay. Now if we had a graphing calculator, we could graph this exactly, because we can plug in lots and lots of points and then we get a nice smooth curve. So this is x equals 3, or sorry, p equals 3. This red line. What about 4? What happens if we take x to the 4th power? Well, this number will be 1/16, even smaller, closer to the axis here. So hard to do because we're getting kind of small for the computer. It'll go through 1, 1, and it will bend up even more. If we take 5/4 and to the 4th power, we can do that here with a calculator. 5/4 to the 4th power is 2.44, which is off of our screen, because we only go up to 2.1. So we're already past this point. So let's just shoot for right around here. So connecting the dots, we have for when p is 4, goes to here, and then up. And what about the left-hand side? Well, now we still have an even power, so we're going to be positive, and we'll have this flatter shape on the interval -1 to 0, similar to the shape on the positive side of the graph, and then a steeper rise due to the higher exponent. And this pattern continues. So what about the fifth power? Well, we have even smaller here. Well, let's write down p equals 4. So the fifth power, we have even smaller here, closer to the axis, and then it comes up to 1, and it'll be even steeper after 1. But on the left-hand side, we go negative because it's an odd power. Like that. And that would be that's p equals 5. So this gives us a sense for the shape of the graphs of power functions that have integer powers. What happens if we have positive integer powers, or 0? What happens if we have a power that's negative? So let's think about the graph of -1. So -1 means the same thing as y equals 1 over x when p is -1. So 1 over 1/2 is 2. What about, and so my idea here about 0 is only true when the power is greater than 0. When the power was 0, remember it didn't go through 0, 0. It goes through 1, the yellow line. And if the power is negative, at 0 we end up with a division by 0. So we have no output when the power is negative. So that's a little important part about this point here, about x equals 0. Y is 0 if the power is greater than 0. Now, when x is 1, all power functions have an output of 1, no matter what the exponent is. If it's negative, positive, fractional, it doesn't matter. We'll see that they all go through this point, 1, 1. When k is 1. Again, that's an important point. So, going back to graphing x to the negative first power, we have at 1/2 we have 2, because it's 1 over 1/2. At 1 we have 1. 1 over 1 is 1. At 2 we have 1/2. And at 3 we have 1/3, which would be about 0.33. It's 0.2, 0.4, so somewhere around here. Connecting the dots, on the right-hand side of the graph, we have, whoa, sorry about that. Let's try this again. The shape kind of like this. Now this curve never touches either axis. It asymptotically approaches, which means as x gets really big, we get really close to 0, but we don't ever get actually to 0. And as x gets really close to 0, but not 0, y gets really, really big. Now what happens on the negative side of the axis? We would have, for -1, 1 over -1 is -1. 1 over -2, sorry, -1/2, 1 over -1/2 is -2. -2, 1 over -2 is -1/2, and 1 over -3 is -1/3. So we end up with this shape reflected on the other side of the graph, the negative side of the graph as well. And this shape happens so much as well in mathematics, it has a special name. This is the case when p is -1, and we call this a hyperbola. And you might even hear someone describe such a curve as hyperbolic. That means a curve shaped like a hyperbola, a 1 over x. Okay, what about more negative powers? What about -2? We end up with y equals x to the -2, which is the same as 1 over x squared. So for 1/2 input, we end up with we get 1 over 1/4, which is 4, which is way up above my graph lines here. So what about 3/4? Let's pick a new color. 3/4, we would have 3/4 squared and 1 over is 1.77. So when the input is 3/4, we get out about here, 1.77. We get 1, 1 again. At 2, we get 1/4, because we have now squared, and here we have 1/9. So you can see we have the same pattern of, now the exponent is smaller, the output has gotten bigger when x is between these, and when it gets past 1, now it's smaller than, because the exponent is smaller. Remember about the values of the power functions on an interval. Let's not erase our axes when we mess up. So again, this gets close but never touches the axis. So we want our graph to represent that. Now what about on the left hand side? Well, when we square, we're going to get rid of the sign. -1 squared will be 1. We'll have 1 over 1. So we'll go through -1, 1. At -3/4, we'll have that positive 1.77 that we found over here. And at -2, we'll have 1/4, and at -3, we'll have 1/9. So we'll end up with a shape that's above the axis that's reflected across the y-axis of this sort of squared hyperbola, which I don't know if it has a name. But this is the shape we get. This is for p equals -2. And just to sketch, if we were to do p equals 3, we would find the curve comes even steeper in. It's going to go even steeper down and closer to the, get to the axis closer. Never touch it. And it will be, since it's odd, on the negative side, the negative y side, when we're -x. This is the shape for p is -3. And then we can keep doing this pattern. When p is -4, we'll come even steeper. And on the left-hand side, will be on the top. So maybe we should graph that one real quick in gray. For p is -4, we're going to come in even steeper, go through 1, 1, come even steeper towards the axis, and come on down. And I'm going to pretend it's behind the orange line. And on this side, the same pattern will hold. We'll come closer to the line here, and we'll come up much steeper on this side. And that's for p is -4. And we can continue to graph this pattern if we want to see all the different kinds of power functions graphed on top of each other for the case when k is 1. Okay, so that candle's positive, 0, the yellow line, negative, which are these hyperbola and hyperbola-like shapes. And then what about fractions? What if we have p is 1/2? If p is 1/2, then we have y is x to the 1/2, which is the square root of x. What does that look like? Well, if we put in 1, we'll have the square root of 1, which is 1. If we put in, say, 4, which is over here, on the edge of the graph, we'll get an output of 2, because the square root of 4 is 2. And what about at 1/2? What's the square root of 1/2? Well, maybe we should think of the square root of 1/4. So that would be the square root of 1/4 would be the square root of 1 over square root of 4, which is just 1/2. So, and then what about negative? If we go negative, we don't have real numbered outputs. So the graph won't have a left-hand side for a fractional exponent. So we don't even think about these other quadrants in this class at all for fractional exponents. So just thinking of the first quadrant, the shape of the graph will be come up, and then we're going to hit 1, 1, same point we always hit, and then we need to go all the way up to this point over here. Okay, this is p is 1/2. Now if you think about this shape, this fractional shape, it looks a lot like the parabola, but flipped across this diagonal line. And that's because it is that shape. And that's because when we take the square root, it gives us the same shape, but the opposite relationship between x and y, right? Because if y is the square root of x, then y squared is x. So you could think of graphing almost the parabola, but the axes are flipped, or the meaning of them is flipped. And we can think of 1/3. The 1/3 power will be steeper. So if we think of 1/3, the 1/3 power will be steeper, just like this was shallower when we cubed. 1/3 will be steeper. We'll actually have the opposite x, y points. So if this was a point x comma y, we'll have y comma x of its same values. It'll go through 1, 1, and then above 1 it'll be shallower because we're taking the cube root. And if we did 4, we would see the same thing. What about negative? We're not going to worry about it. Now there is a negative to the cube root, which I'll go ahead and draw. If we had negative 1/3, we would actually have these legal values because we're allowed to put in negatives and we would get out the negative counterpart. But for the squared, we don't. So generally, we don't think of the fractional powers with a negative value. What about the 3/2 power? How would that look? If we have p, oh, I didn't write this down. P, so the red line is p is 1/3. If we have the 3/2 power, so if we have y equals x to the 3/2, that would give us the square root of x cubed. So if we put in 1/4, we would get 1/2 is the square root, and then cubed, which is 1/8, so which is right here. Okay. If we put in 1, we get out 1. If we put in 4, we would get out 2 cubed is 8, which is off of our chart. So let's use some calculating here. What if we put in 2? We would get the square root of 2, square root of 2 to the 3rd power, 2.8, which is off of our graph. So let's try 1.5. We take the square root of 1.5 and raise it to the 3rd power, we get 1.83. So if we put in 1.5, we get out 1.83. So 1.5, 1.83 is close to this point here. So our line would go kind of a curve to 1, 1, like they all do, and it will come here. And if you notice, this is p is 3/2. It's in between p is 1 and p is 2, which is the blue line. And that's going to be the pattern for any fractional powers. They're going to fall in between the lines for the whole numbers that are between the fraction. So this gives us an idea of the shape of the various power functions when k is 1. And when k is 2 or 7, we just multiply the y value by 2 or 7. So it just changes the scale. The shape would really stay the same. So let's do some examples now after having talked about the principles behind power functions. The weight W in pounds of an astronaut is inversely proportional to r squared, where r is in thousands of miles. And I think we're missing here from this problem, r is the distance from the center of the Earth. Okay. If the Earth's surface is roughly 4,000 miles from the center, and an astronaut weighs 180 pounds on the surface, what is the constant of proportionality? Okay, so first of all, let's write an equation from the statement above. The weight W is inversely proportional to r squared. Okay, so we know the weight is the constant, some constant times r to the negative 1/2, which we can think of as dividing by r squared. Right, these are equivalent by the rules of exponents. So we know that when the astronaut is at the surface of the Earth, he weighs, or she weighs, 180 pounds. And we know that they're roughly 4,000 miles from that center. So we need to find k, the constant of proportionality. So we do some arithmetic here. We have 180 times 4,000 times 4,000 is k, or 2.88 times 10 to the third. To the third power. Okay. Now, sorry, third. That's not right. 10 to the ninth. We were in billions, right? It was 2,888,000,000. So it's 2.88 times 10 to the ninth power. So now we need to, that's part A, so k is 2.88 billion. And what's the units for k? Well, it would be miles times miles times pounds. So it would be pounds times miles squared. Okay, so when you divide by miles squared, you get pounds out. I just took the units for this, and since we multiplied because of the inverse relationship, the units of this squared, that's would be the units of the constant. Maybe not so important in algebra, but in the context of physics, we would want to know the units of these constants. That's important in case we need to convert. So if this is the constant with miles, what if we need kilometers? So we need to convert miles squared to kilometers squared. That's part A. Part B, how much does the same astronaut weigh 1,000 miles above the surface of the Earth? So the weight would be the 2.88 times 10 to the ninth power is our constant divided by r squared. R, remember, is the distance from the center of the Earth. This is 1,000 from the surface, so we need to add 1,000 to 4,000 to get 5,000 squared. So using a calculator, 2.88 times 10 to the ninth divided by 5,000 times 5,000, or 5,000 squared, is 115.2. 115.2 pounds. Now, this might make little sense to you because you might be thinking astronauts don't weigh anything when they are orbiting the Earth, which has to do with the fact that when you're orbiting the Earth, this is kind of an aside, when you're orbiting the Earth, you're actually falling. So it's kind of like being in an elevator that's falling, or anything that's falling. If you were, or an airplane that's falling, if you're falling with the things around you, there is no gravity, so to speak. There's no force pulling you down to the thing that's next to you, so you feel like you're weightless. This is very similar to neutral buoyancy. If you're in the water and you offset the force of gravity pulling you down with the force of buoyancy, you essentially float, and there's no force on you, which is essentially what happens when you're in free fall in Earth's orbit. Now, if you were actually resting on something resting on the Earth that was 1,000 miles up, then you would weigh 115.2 pounds. You'd have this force pulling you down from the Earth as you're standing still. But when you're moving around the Earth, you still have this force pulling you down, but you also have a force that's taking you this direction. Okay, that is what causes this situation, which we can talk more about in physics when we talk about gravity. Power functions. more about them. So let's do this other example. For each pair of numbers, determine which one is greater. So here we can either think back to the graphs or think to the principle on the interval between 0 and 1. If k is the same for the two functions, then the first is less than the second if the power of the first is bigger than the power of the second, right? Or I think the way it was stated was the other way around. If the powers are less, the first is bigger. Okay, so essentially whichever one has the less power when we're between 0 and 1 will be the bigger, but when we're above 1, we'll have the opposite. F is bigger than G if and only if P1's bigger than P2. Okay, so for 3 and 3 to the 1/2, the bigger will be the one with the bigger power, since 3 is bigger than 1. So the base is bigger than 1. So in this case, the answer is 3. But if we're between 0 and 1, as in 0.3, the answer would be, maybe we'll just underline or square the one that's bigger. The answer will be the one with the smaller power when we're between 1 and 0. Here we have bigger than 1 for the input, and so the one with the bigger power is the bigger, which is 3/3 is bigger than 1. And here we have a smaller between 0 and 1 base, which means the one with the smaller power will be bigger, which is 0.3.